A very good afternoon, class 12th. Moving on with the second part of the VSEPR theory. Now in this case, again, as I did in the last part 1 of the video, the theory is responsible for the shapes of covalent molecules. But this time, we are talking about only those molecules which have got the central atom with lone pairs. Now, what are lone pairs? Lone pair are the non-bonded electron pairs, which means the central atom, the 2 electrons or 4 electrons which are not used up in forming the covalent bond. That means they have been not utilized for forming the mutual sharing. Fine. Now, the important notes that you require for this particular section of the VSEPR are: the presence of these lone pairs on the central atom causes a greater repulsion. Hence, you need to be placing them at a larger bond angle. So, whenever there is a choice of the geometry where there are more than one type of bond angles associated, you will try and put the lone pairs at that position जहाँ पर angle बड़ा हो. Angle बड़ा होने से repulsion कम होगा. So, please place the lone pairs in a way that they are at a position of higher or greater bond angle around the central atom. Fine. Now when we talk about the magnitudes of repulsions, now under the category of magnitudes of repulsion, it is found that lone pairs to lone pair repulsion is maximum. Next come into the category is lone pair repulsion with the bond pair, and the least of all is the bond pair repulsion. Which means when we are talking about bond pair repulsion, since it is the minimum repulsion, therefore we prefer that this is the position with stability. Presence of a lone pair always leads to instability in the molecule. Fine. Moving to the last section. In the part 1, I always said that geometry and the shape remain the same. The reason being, when we have got only bond pairs, then geometry and the shape is same. But in case of molecules where there are lone pairs, then for the geometry of the molecule, you take into account all the electron pairs. As we did in the part 1, we only had electron pairs as bond pairs. So, geometry and the shape were same. But when you talk about the shape of the molecule, you only take the bond pairs. Please remember, ignore the lone pairs. The shape is decided by ignoring the lone pairs. Now moving on with the examples. The first category of example is your central atom has 3 electron pairs and it has those 3 electron pairs. The geometry is for AB3, which we have already done for BF3 in the part 1 of the video. Now, in this part, since I am looking for molecules with lone pairs, so I am talking about a situation where you have only 2 bond pairs and 1 is a lone pair. B is referring to the bond pairs and L is referring to the lone pairs. Let's think about such an example. Under this category, the example is SO2. Now, in an SO2 molecule, the central atom is S. It has got 6 electrons. Out of these 6 electrons, 2 electrons are used by one oxygen, 2 electrons are used by the other oxygen to form double bond each. You are left with 2 electrons which are left. These 2 electrons are called as one lone pair. Therefore, this geometry has 2 double bonds around the sulfur and 1 is a lone pair. And you already know double bond is considered as a single superbond pair. So, when we have a central atom with 3 identities around it, this is the geometry when we talk about something like BF3. Central atom with 3 bond pairs and the angle should be 120 on each. Now, if you have to place one of them as lone pairs. Now, this is my electron cloud, which I am saying is the lone pair. Now, if I place the lone pair like this, as already said, lone pair causes a greater repulsion. Now, if it causes a greater repulsion towards the bond pairs, so under these circumstances, the bond pairs move slightly closer. So, this angle no more is 120 in the presence of the lone pair. So when you write about SO2 molecules, for SO2 molecule your illustration would be sulfur having a double bond with oxygen, and it has a lone pair of electron represented like a cloud. And you should understand that this bond angle is less than 120 due to repulsion between lone pair and bond pair. Fine. Now let's talk about the geometry. As said, the geometry is triangular planar. Because for geometry you include all type of electron pairs. But for the same molecule, if you are asked the shape, then please remember lone pair is not to be included. Now if you don't include this lone pair, what are you left with? You are left with only these three. Which means if I remove the lone pair here, what am I left with? Only these three. Now this geometry without the lone pair, when you talk about the shape without the lone pair, we call it to be a bent shape or an angular shape or a V shape. This is represented as a V shape or a bent shape or an angular shape. Is that okay? Moving to the next example now. The next category is when your central atom has got 4 electron pairs around it. Now whenever there are 4 electron pairs, then your geometry will always be tetrahedral and the angle expected is 109.5 degrees. But this is only if you have all the 4 to be bond pairs, as we did for a methane molecule in the part 1. So for a methane molecule, this yellow ball represents the carbon and the 4 balls of blue color represent the hydrogen, and that is how the geometry looked like. Now in this class we are going to talk about the presence of a lone pair. Now when I talk about the presence of a lone pair, which means I need to replace the bond pair by a lone pair. Hence the first category under this example is AB3L, which means around the central atom you have 3 bond pairs and 1 lone pair. Let me take this example first. If around the central atom you have 3 bond pairs and 1 bond pair, the example can be NH3, it can be PF3, it can be PCl3, it can be NF3. Now under all this category, let me take one example as NF3, or I can take it as NH3 also. So let me focus first of all on NH3. Now when I talk about NH3, which is the central atom? The central atom is nitrogen. Nitrogen has 5 electrons, out of which 3 electrons are used for bond pairs with 3 hydrogens. What are you left with? 2 electrons left. Therefore 1 lone pair. So you have 3 bond pairs and 1 lone pair. So the geometry has to be like tetrahedral. So this is your tetrahedral had it been 4 bond pairs. Now one of the positions, now all the positions are equal. I did say lone pair is to be placed at a position where the bond angle is larger. But in a tetrahedral, all bond angles are 109.5. So you can place your lone pair anywhere. I am replacing the top position with the lone pair. So that's how the geometry looks like. If I replace the top position with the lone pair, the effect of this lone pair is felt by these 3 bonds, and we find that these 3 bonds move closer to each other, which means this angle reduces. Owing to the presence of this lone pair, the lone pair causes these angles to reduce because the lone pair repels them strongly. So representing this with ammonia, this is my nitrogen. I have 3 bonds with hydrogens in a 3 dimension. This is the plane, and I have 1 lone pair on nitrogen. As already said, lone pair bond pair repulsion is greater than bond pair. Therefore this lone pair repels these bond pairs strongly. Hence these hydrogens move closer. Hence this particular bond angle is less than 109.5 and it is equal to around 107 degrees, which you should remember for ammonia. So when we talk about the geometry, this is how it looks like. It is a tetrahedral with a lone pair. It is not a proper tetrahedral. We say that this geometry is a distorted tetrahedral, because a proper tetrahedral should have angle as 109.5. But here, due to the presence of the lone pair, the angle gets distorted. So the geometry is distorted tetrahedral. Now, when I talk about the shape, as I already said, for the shape, you do not take into account the lone pair. So without the lone pair, what is the shape like? The shape is like a triangular pyramidal. So we call the shape as a triangular pyramidal. Now, this is applicable for all these molecules, because in all of them, your central atom has got 5 electrons. So even for SbH3, that is antimony, or for arsenic F3, for all of them, the geometry will be same. So all group 15 members with 3 bond pairs will have a geometry of triangular pyramidal a shape of triangular pyramidal and a geometry of distorted tetrahedral, owing to the presence of this lone pair. But the angle decreases from 109.5, which is only 107 is only for ammonia. This is what you need to learn. But for other molecules, you will only say that the angle is less than 109.5. You will not say that it is 107. Fine? Now, under this category, there is a special example where you have AB3L. Now, this is an example called as XeO3, which is a surprise, because xenon is a noble gas. But out of all the noble gases, xenon is a noble gas, but out of all the noble gases, this is the largest. Therefore, comparatively, the ionization energy of xenon is going to be lower as compared to others. Hence, its electron is utilized for bonding with only oxygen and fluorine. Why? Because oxygen and fluorine are highly electronegative. Since these are highly electronegative, they can form compounds with noble gases. The noble gases that we know of are helium, neon, argon, krypton and xenon. Out of all these noble gases, no compounds are found for these 3. Just a single compound is formed for krypton as krypton difluoride, and xenon forms many compounds. But all of them are with oxygen and fluorine only, because oxygen and fluorine are capable of utilizing its electrons for bonding. Fine. So we move on to the special example under this category, which is xenon trioxide. Now in this case, xenon has 8 electrons, out of which utilized electrons are 6 electrons, 2 electrons each for oxygens, which means you are left with 2 electrons are left. So you have 1 lone pair and you have 3 double bonds. Fine. So your xenon has 1 double bond, 1 double bond, 1 double bond and a lone pair. That's the situation. Now let's talk about the structure. Now as already said, a double bond is considered as a super bond pair. So your xenon molecule having 3 oxygens would look like this. These are the 3 oxygens and you have 1 lone pair to be placed, which will be placed like this. So you have a structure similar to ammonia with 3 double bonds as with oxygen as blue colored, and 1 is the lone pair on top. So the geometry is exactly like ammonia. Let me draw it for you. This is your xenon, a double bond here, a double bond here, a double bond here, and you have a lone pair on top. Fine. Now this is the structure or the shape of the molecule, and because of this lone pair pushes them below. So when you talk about this particular angle, you would only say less than 109.5. Nothing else would be said because you cannot remember all the bond angles. So only mention that it is less than 109.5. Again in this molecule, if you are asked for the geometry, the answer would be distorted tetrahedral. And if you are asked for the shape is going to be Trigonal Pyramidal, because the shape is decided in the absence of the lone pair. So in the absence of a lone pair, it is like a triangular or a trigonal pyramidal. Is that fine? Moving on to the next category. Which is AB2L2, where the central atom has 2 bond pairs and 2 lone pairs. Now before I take the example of it, let me explain how will it look like. Now, had it been 4 bond pairs, your central atom would have been tetrahedral like this. But if there are only 2 bond pairs, so remove these 2 bond pairs and replace them by lone pairs. This is one lone pair and this is the other lone pair. So this is how it will look like. But we very well know that the lone pairs repel each other strongly. So since they would repel each other, they will move away and they will cause these 2 bonds to move closer. So the angle further decreases. And when we talk about this shape, it is a distorted tetrahedral. Sorry, a geometry is distorted tetrahedral. But if we want to talk about the shape of the molecule, you will not talk about the lone pairs. In the absence of lone pair, this is how the geometry will look like, which is nothing but a bent or an angular or a V shape. Otherwise, the geometry would be called as distorted tetrahedral. Let me take up a special example under this case. The example for this second category is where you have AB2L2. There are 2 bond pairs and 2 lone pairs. Example for this category can be water. It can be H2S also, that is hydrogen sulfide gas. Now let me take this as an example. Now in this case, your central atom is oxygen. Now oxygen has how many valence electrons? 6. Out of these 6 electrons, how many have been used? 2 electrons by 2 hydrogens. What are you left with? 4 electrons are left. These 4 electrons therefore make it 2 lone pairs. So you have 2 bond pairs and 2 lone pairs. How do you represent it on paper? Now this is your oxygen atom. You have a situation where it is like this, the tetrahedral geometry, out of which I place 2 hydrogens here and I place the lone pairs here. So these are the lone pairs which cause the repulsive interactions, and this repulsion between the lone pairs is high, which causes this to push the bond pairs closer. So this angle is much less than 109.5 due to 2 lone pairs causing excessive repulsion. Also, this angle, you should learn it up. The angle here, only in case of water, is 104.5 degrees, which should be known to you people. The similar case, when you talk about the geometry in this case, as I already said, the geometry in this case will include bond pairs and lone pairs both. So the geometry is distorted. Distorted matlab kharab. Distorted tetrahedral. It is not a normal tetrahedral with an angle of 109.5. It is distorted because the angles have reduced. And we say the shape, when we talk about the shape of this molecule, you can call it to be bent, you can call it to be angular, you can call it to be V-shaped. Because when we talk about the shape, you ignore the lone pairs. So what are you left with? Only this much. And this is nothing but a bent or a angular geometry. The same thing can be drawn by you people for H2S. Take sulfur as the central atom. Now we have the central atom having 5 electron pairs around it. Now, if the central atom has 5 electron pairs around it, we already know the geometry would be trigonal bipyramidal. In this particular geometry, there are two different types of angles. These angles in the plane are 120, while the angle on top is 90 with these three, and angle at the bottom is also 90. So this is the first geometry where you have an option of two types of bond angles, 120 and 90. Now, if at all there is a lone pair in such a molecule, where do you think will you place it? On the top and the bottom where the angle is 90, or in this yellow plane where the angle is 120? Think. The answer is you will place the lone pairs always on this equatorial plane. The reason being, on the equatorial plane the bond angle is 120, larger than 90, so it will cause lesser repulsive interactions. So AB5 we have already done. Let's move to a category where you have 4 bond pairs and 1 lone pairs. The example is SF4. This is commonly asked in examination, so you should be thorough with this. The central atom is sulfur. It has got 6 electrons. 4 electrons are used in bond pairs. You are left with 2 electrons left, which is nothing but 1 lone pair. So you have 5 in all. Now when we talk about this geometry, how do I draw it? So this is your sulfur. This is the trigonal bipyramidal geometry, because you have to place 5 electron pairs. Fine. Now out of these 5 electron pairs, I need to place 1 lone pair, and the lone pair will be placed on the equatorial plane because the bond angle here is larger. You can place your 4 fluorines like this. Now this lone pair will also cause this angle to decrease. So the angles will be less than 120, and these will also be pushed back. Fine. So we call this geometry as a seesaw geometry. Now why do we call it as a seesaw geometry? Let me rotate this molecule like this. If I turn this molecule like this, you should understand the geometry would be something like this. I have just rotated the molecule for better understanding. Fine. This molecule I have just rotated it for better understanding. Can you see this shape which I have drawn is something like the swing seesaw which the kids play with. Okay, so that's the reason this shape is the name given for this particular one. Otherwise, if you are asked the geometry includes all lone pair and bond pairs. So the geometry is said to be trigonal bipyramidal. But for the shape, we talk about not the lone pair, only the bond pairs, and it is said to be a seesaw shape. Fine, understood? Now, in case of 5 electron pairs, if you have 3 of them are bond pairs and 2 of them are lone pairs. So in this geometry, where you have 5 positionings possible, you have to place the 2 lone pairs. As already told, they cause a high repulsion, so the lone pairs have to be placed in any of the 2 positions on the equatorial plane due to the larger angle of 120. Rest 3 positions will be taken by the bond pair. The example under this category is ClF3 or BrF3 fall under this category. Now let me take ClF3 as an example. Cl has 7 electrons, out of which it has used 3 electrons with 3 fluorines, so 3 bond pairs. You are left with 4 electrons, which is equal to 2 lone pairs. Now in this geometry, how do I draw it? A similar method. You have your Cl, you have to place 5 electron pairs around it. 3 are bond pairs and 2 are lone pairs. Now in this geometry, the lone pairs will always be placed at a higher angle. So this is one lone pair, this is the other lone pair. What am I left with? 3 fluorines to be placed. 1 fluorine here, 1 fluorine here, and 1 fluorine here. This geometry is called as the T-shaped geometry. This along with this line, this and this line, it is said to be a T-shaped geometry, and the shape is T-shaped and the geometry is trigonal bipyramidal. The same thing I'll draw it for BrF5 also for a better understanding. The situation remains the same. Br has 7 electrons, out of which it has used 3 electrons for 3 bond pairs, and you are left with 4 electrons, so you have 2 lone pairs. So this is your bromine with 3 bond pairs to be placed and 2 lone pairs to be placed. I think you will understand this slightly better if I place the lone pairs here. These are my 2 lone pairs placed on the equatorial plane, while the fluorines are placed like this. I hope the T shape is now better understood. So the shape is T-shaped, but the geometry remains the same in both the cases. Fine. So this was under the category of 5 electron pairs when there are lone pairs involved. A special noble gas compound under this category is XeF2 or krypton difluoride. Both fall under the same category. Now let me take this example up. Xenon has got 8 electrons, out of which you have used only 2 electrons for 2 bond pairs. What am I left with? 6 electrons are left. That means it has 3 lone pairs. So the number is again 5. So you would have, this is the geometry where you have trigonal bipyramidal geometry. You have to place 3 lone pairs this time. And all the 3 lone pairs will be placed on this plane. None of them will be placed on top and bottom because this is the plane with 120 angle. So when we draw this structure, you have your xenon with 3 bonds in the plane, 1 bond above and 1 bond below. Now the 3 lone pairs, mind you, lone pair cause greater repulsion. Since they cause greater repulsion, to avoid that, we place them at a larger bond angle. So your 3 lone pairs are placed here because the angle here is 120, while your fluorines will be placed on top and bottom. Now having a look at this, the geometry includes all bond pairs and lone pairs. So the geometry is trigonal bipyramidal. But if you are asked the shape, for the shape, please ignore the lone pairs. If you don't see the lone pairs, what are you left with? Just a line. So the shape is linear with bond angle of 180 degrees. Fine. Exactly same is applicable to krypton difluoride also, which I hope you can do it on your own. Moving on to the next category. The next category we have, the central atom has got 6 electron pairs around it. We've already done this. If the central atom has 6 electron pairs, then 4 of them are in this square plane. 1 is on top and 1 is below. So this is how you place the 6. The geometry is, in that case, is octahedral, the shape and the geometry, and all angles are 90. Now since all angles are 90, you don't need to worry where to place the lone pairs. But I would advise, please keep lone pairs on top or bottom position, just for better understanding, no other reason. Otherwise, angles are all 90. You can place it anywhere that you want. The answer should be correct. You should be marked fully. But my advice is, please place the lone pair on top and the bottom to understand the shape a little better. Under this category, the first example category is, instead of 6 bond pairs, which we have already done, which was your SF6, which was already done in the part 1, we move to the second geometry where you have the central atom with 5 bond pairs and there is 1 lone pair. So if there are 5 bond pairs and 1 lone pair, the example under this category is BrF5. The central atom is bromine with 7 electrons, out of which you have used 5 electrons for 5 bond pairs and you are left with 2 electrons for 1 lone pair. So total of 6. So if you have 6 electron pairs around bromine, the situation would be that of octahedral. 1, 2, 3 and 4. For 6 electron pairs, this is how you arrange your geometry. Now in this geometry, you have to place only 1 lone pair. All positions are at an angle of 90. So you can place your lone pair anywhere. But as I said, please try to place the lone pair on top and bottom for better understanding. So I am placing the lone pair here. This is the electron pair of the lone pair. This is how also you will find it in books. You are left with the 4 fluorines. Fine. Now in this case, the geometry in this case remains octahedral, of course distorted, but the shape will be without the lone pair. If I ignore the lone pair, what am I left with? A square pyramidal. So it is a square pyramidal. Now as far as CBSE is concerned, it's okay. But if I talk about entrance, do you understand that this lone pair will also repel these 4 bonds? Which means actually in this case your Br will have 1F on top and these 4 would also slightly move up. So none of the bond angles should be at 90 owing to this presence of the lone pair at the bottom. So these angles, as you can see, are affected by the lone pairs and they move slightly up. Fine. So actually no angle is 90 degrees actually, but the CBSE doesn't give this. CBSE says, does not talk about this repulsive interactions. So it gives you the shape as square pyramidal. Fine. Moving on to the next category under the same. The third category in the theme is central atom has 4 bond pairs and 2 lone pairs. Now if that is the case, if it has 4 bond pairs and 2 lone pairs, there are total again 6 electron pairs to be placed. And when you place these 6 electron pairs, you require the octahedral geometry. Out of these 6 positions, you have to place 2 lone pairs. You can place the lone pairs anywhere that you like. But my advice is that you place them on top and bottom for better understanding of the geometry. Under this category, the special example is your XeF4. It is a xenon compound, XeF4. Here you have xenon as the central atom with 8 electrons. Out of 8 electrons, 4 electrons are used for 4 bond pairs with 4 fluorines. Rest 4 electrons are nothing but 2 lone pairs. Fine. So the geometry expected is octahedral. 1, 2, 3 and 4 bonds to be formed. Fine. Out of these 6 bonds, you have to place 2 lone pairs. As I said, all angles are 90. You can place the lone pair anywhere that you like. But the advice is, please place it at the top and the bottom. So I've placed the lone pair on top and bottom. Now, rest are the 4 fluorines. The 4 fluorines are kept here. Now, can you clearly see? The shape becomes square planar. Square planar shape can only be understood if you place the lone pairs like this. Otherwise, it will be difficult for you to understand this particular shape. As far as the geometry is concerned, is octahedral. But the shape is square planar owing to the presence of the 2 lone pairs. Is that fine? Moving on to the last category of today's class, when you have 7 electron pairs around the central atom. In such a case, we have already done in part 1, the geometry is Pentagonal Bipyramidal, 1 on top, 1 below, and in the plane you have 5 bonds. Now, under this category, you have A, B, 7. We already did IF7 in the first video. Now, in this category, I am talking about A, B, 6 and there is 1 lone pair. There are 6 bond pairs and 1 lone pair. So, you expect the geometry to be A is your central atom and there are 5 bonds like this, 3, 4 and 5 in the pentagonal planar shape. 1 bond is above and 1 bond is below. I've just used a different color for better clarity. Now you very well know this angle is 72 degrees while this angle is 90 degrees. So if I have to place a lone pair, it will go at the 90 degree. So your lone pair takes this position. Fine. Now you are left with the 6 B atoms. 1, 2, 3, 4, 5, 6. So it looks like this. But this geometry has been ruled out. The reason being, this is highly unstable. Why? Because of 72 degrees, the bond pair repulsion is high. So this geometry is ruled out. Instead, surprisingly, The geometry that is existing in such a molecule is, you have a central atom A, there are 6 B's in the octahedral geometry, all angles to be 90. But now where is the lone pair? Surprisingly, this lone pair is placed like this. What do I mean by this? Which means this lone pair has no particular place. It is not localized. It is said to be delocalized. Means it is hovering over the whole molecule and its effect is all over on the molecule. What do we gain by this? Now all angles are 90 degrees. This leads to a better stability. Under this category, the example that you should know is that of XeF6. The only example under this category is XeF6. As you can see, in this case, your xenon has got 8 electrons. 6 electrons you have used for 6 bond pairs. 2 electrons you are used for 1 lone pair. So please draw it exactly like this. I'll just draw it for you. In this case, you would be drawing it something like this. This is your xenon. You need to draw 6 fluorines around it. 1, 2, 3, 4, 5 and 6. And you need to draw 1 lone pair, which you can place anywhere. You can place it like this also. So this is your lone pair, which is delocalized. We call the shape to be octahedral, and the geometry is also octahedral, but it is distorted when you talk about the geometry. Fine. So with this, I come to the end of the VSEPR theory. The next video would be on dipole moment. Please keep watching, sharing and liking this particular channel. Bless you loads, kids. Do well in life. Do awesomely well in life. Stay safe. Stay healthy. Bye.